Okay, well, you see the project's called XMed. It's about turbines and simple wave energy device. It's basically it's going to be a quick gallop. But first of all, people. There's been a lot of people involved. The project's actually finished, although much of it has been written up, and some experiments actually in Edinburgh are continuing. But you can see a lot of people involved, 4 PhDs. And all of them, I believe, are still working in either marine or wind energy. So this is going to be a pretty quick gallop. So the objectives were with tidal stream turbines, and I should say that Tim Stallard, who actually was supposed to be here but isn't, was in charge of this really. It's about tidal turbulence, wake turbulence, swell wave loading, and impact of things. And the wave part was considering a simple torque-moored floating body, which we'll come to at the end, and some very nice experiments done at Plymouth and some computer modelling done at Plymouth and Manchester. So this is just a diagram of the arrangement here. You can see everything going on. We've got arrays, we've got turbulence, we've got these waves are going to be affected by arrays, which was part of Olsak's thesis, which was quite interesting. And so the whole sort of effect on thrust and power has been looked at. Been a lot of work done on using LES, large eddy simulation, which is massive computational effort. This was very much mixed up with the project called REDAT, which is the ETI project involving the Alstom turbine in EMEC. And so basically, these are just some results. There's masses of results. But if we don't put any turbulence in the onset flow, this is the arrangement that we have idealized as. Well, this is the actual turbine. And you can see these tip vortices coming off, and you can see the complicated business of flow around the support, and we'll see some spectra in a minute. And of course, what we really have is turbulence coming in, this is obviously a vertical plane in line with the flow, and this is a cross plane of the turbulence. These colours are velocity, and you can see that the wave has changed a bit. The actual tip vortices break down more quickly, and the interaction with the support is more complicated. And this was reported in UTEC recently. I should point out that these runs were done on the EDF computer Blue Gene in Paris, which we made a very generous sort of contribution to all this. This is quite an important slide, one of many, of course. This is the spectrum of the root bending moment, and comparing with the measured data with LES with no turbulence and LES with the full turbulence represented. The run, frankly, wasn't long enough. We really need to do about 5 or 6 more rotations to get better statistics. But you can see, well, maybe you can see, the black line is the measured, the purple line is the best computation. It's a bit sort of spiky, but that's because we really need to have more rotations to get better data. And you can see the origins of the various sources of fluctuation on the blade, which is obviously very important for fatigue. So reasonable agreement. And this isn't the final thing, but it's not far off. We did some experiments with, basically this is in the small flume in Manchester, 5 metres wide, half a metre deep, or 0.45 metres deep, and basically looked at the thrust, and this is obviously extreme value probability plot, a Pareto type, and basically you can see how the 1 in 100, 1 in 1,000, 1 in 10,000 changes relative to the mean, which is F0. This should be relative to the mean there, and it depends on the turbulence intensity. This is 12%, and that is 17%. And with more experiments have been done, running for as long as we're legally allowed to run under health and safety, which is 8 hours. So it's an order of magnitude longer runs. So we'll be going to 1 in sort of 100,000 shortly. If you put on waves, you might think this is rather complicated. it actually turns out to be quite sort of simple, because basically the extreme loads, if you add waves, these are just for waves in line with the current direction but opposing it, and basically you get the extreme force, which are these values along here, for different probabilities, are simply given by what you get in a current plus a bit due to the wave. Actually, that's wrong. But anyway, so you have a very simple thing. You just add on the extra forcing due to the wave, but with a drag coefficient which is different from the thrust coefficient. Some more work is being done on the effective scale. This is something which has been built actually in Edinburgh with Greg Payne and Tim have been particularly involved. I've been watching. And this device now, which is, you can see 1.2 metres, about 1 in 8 scale typically. It's been tested in IFRMA and reported in UTEC. The aim is to look at turbulence waves and how this thing scales with the experiments in Manchester, which is smaller scale, and possibly also the full scale in EMEC. Very nice thing. I think it works very well. And these are just some results which are far too complicated to take in 10 seconds. But basically, you can see there's some results. You can see these red lines here are the deviations from the mean, and the bigger as the turbulence is bigger, 12% as distinct from 3%. So that's and there's some BEM results compared. Okay, and some vertical wake. Well, some velocity deficit measurements both in the cross plane and in the vertical plane. Again, for comparing with smaller scale results, which will be quite interesting. One of the things that's going to be done, which hasn't been done yet, but I think is planned, is that we're going to look at the impact of things hitting this blade. This is Gregory Payne's rig here. This is the obstacle of various types, and this is basically the blade which is going to hit this thing, and the loads are going to be measured. So some rather careful experiments have been done there, looking at repeatability. This is the thing we're going to model, and the impact forces are dependent on how you actually model it, whether it's this thing with a rubber skin or this thing with a hard bit of plastic substance, which is what you get in the head, but over this bit here you get a much sort of more softer rubbery thing. Anyway, so this is in hand. Some computational modelling has been done, which you'll see at the end, but the experiments will be very interesting, I'm sure. Quickly on to arrays. Been quite a lot of work done on arrays, both the mean flows and forces, but also more recently the the fluctuating thrusts on one turbine in the wake of another. This is 3, 4, 5 turbines, 4 diameter spacings, and this is the results of a comparison with Iran's BEM prediction, also done by Alex Olczak, who is a PhD funded by SuperGen, and you can see the agreement is not perfect, but it's not that bad. We've also got some other faster ways of doing this, which we won't go into in the interest of time. So there's been quite a lot done on that, but as I say, been some very detailed measurements of one turbine downstream of another. Again, it's 8 hours business to get the full range of probability of what the extreme loads actually are. That's been done but not written up yet. And now finally, on to waves. Torque moored buoy. This is the coast, well, you can only see a bit of it. This is the coast facility in Plymouth. This is the buoy moored to the seabed. It's a hemispherical base and a vertical side thing. And the elastic properties of this mooring line are well defined, which is rather important. And basically, it's concentrated on focus waves. We're interested in extreme waves here. This is obviously a braking one, but there've been non-braking ones as well. It's been published in this paper by Martin Han and people. So some CFD has been done, and I should point out a very wide range of conditions has been looked at, which is in the paper. all quite interesting because the biggest forces don't always correspond with the biggest responses and all that sort of thing. And the biggest waves don't always give the biggest forces. So actually it's really rather, to do a design, there's a lot of scenarios to look at. Anyway, so Plymouth have used open foam and get these sort of, this is open foam, and they get these quite good results when there's no snatching. And this is Ransley's PhD. We've been doing some SPH runs in Manchester. Video works, this is great. It's called incompressible SPH, which gives nice smooth pressures. But the plan here is not to model the complete flow, which is very computationally expensive, but just to model the wave and then get what's called the Frag-Krylov force, or the forces due to the pressures in the ambient flow, and guess the added mass, or at least you've got empirical values for that. So this cuts computer time by, well, probably 2 orders of magnitude. So this particular run takes an hour or so on a desktop, standard desktop. And the question is, does it work? Well, the answer is remarkably well. It works, I'm not showing the results, but it works for non-snatch loads, which is fairly smooth waves, but with snatch loads, you can see we're getting these effects really quite well. When the waves are breaking, we actually overestimate with this approach by about 30%. Interesting point here is that these results are quite insensitive to the artificial added mass that you actually put in. These are acknowledgements, thanks, and questions. And this is just to remind us that we're still going to be doing, it breaks here somewhere, that we're still going to be doing this sort of thing in flow wave. But that's a computer animation, I should point out.
This production is brought to you by the University of Edinburgh.